Hello everybody and welcome back. We are still looking at page 5 in the workbook here. So we have a lot of definitions behind us now, and so we're ready to put these definitions to work and to start talking about some theorems, some things that are true, some basic properties of matrices. Okay, and we'll start with Theorem 1.0.6, basically just a big long list of properties that matrices have to have. So we're starting with three matrices A, B, and C, and we're going to let C be a scalar. And turns out that all of the properties on this list are true, provided that the matrices have the correct sizes, so that the sums and the products that you see make sense. So let's start with number 1, for example. A plus B equals B plus A. This is just telling us that it doesn't matter what order you add matrices in, you'll get the same thing. Does anybody remember a name for this property? Okay, you might remember hearing the word commutative. Okay, so it's telling us that matrix addition is commutative. Okay, and the second one, A plus B plus C is equal to A plus B grouped together plus C. That's called associativity of addition. Okay, and 3 is similar. That's associativity, this time of matrix multiplication. Okay, we'll talk about, give a name to one more of these. So property 4, basically telling us that we can, if we have A times B plus C, we can distribute the A through and expand it as AB plus AC. Does anybody remember a name for that property? Okay, that's called distributivity. Okay, and we could go down this list and maybe give names to the rest of those. That's not so important, though, in the grand scheme of things. What we would like to focus on is how would we prove a property like this? Okay, we have some nice definitions of the basic matrix operations, so we could use those definitions to prove any property on this list that we have here. Okay, we're going to focus just on one of the properties for now. Okay, so let's clear a little clutter away here. We would like to prove property number 1 on this list. Okay, the commutativity of matrix addition. Okay, so here's the strategy that we're going to use, okay, in this class when we prove things about matrices. Okay, to say that two matrices are the same is really saying that all of the corresponding entries in the matrices are the same. So our strategy is going to be to take an arbitrary entry in A plus B and show that it's equal to the corresponding entry in B plus A. Okay, so we might start our proof then like this. So let A and B be any m by n matrices. We need those to be the same size, okay, so that matrix addition is defined. Okay, and then as I just said, we're gonna pick on an arbitrary entry in the matrix A plus B. Okay, so for any I and j, that's going to be kind of the name for our row number and column number. Okay, with I between 1 and m, and j between 1 and n. Okay, because basically I is representing column number, or I'm sorry, row number, and j is representing column number. We have, okay, we're going to look at the entry in the ith row and the jth column of A plus B. What we need to show is that's the same number as the entry in the ith row and the jth column of B plus A, and we'll prove that in a sequence of steps here. So let's start with the definition that we have of this. Okay, it tells us that we can get that entry by taking Aij plus Bij. That was just our definition of matrix addition. Okay, specifically definition 1.0.2. Okay, but then I claim that we can change the order of those two entries. We can write that as Bij plus Aij. How do we know that we can do that? Well, basically what we're using here is the fact that these two numbers, they're not matrices anymore. Those are just real numbers. They're entries in our matrix. And we know that addition of scalars is commutative. So if we want to give a reason here, we could just say commutativity of scalar addition. Okay, and I emphasize the word scalar. Okay, so in this course, we'll assume the basic properties about the real numbers. Okay, so anything that you learned in your arithmetic class about ordinary real numbers, you can use in here. Okay, and then finally, bij plus aij, that is by definition the entry in the ith row and the jth column of b plus a. So we've just used definition 1.0.2 again. Okay, this time for the matrix b plus a. So notice where we started and where we stopped. Okay, we just showed that in the matrix a plus b, in the matrix b plus a, you get the same number in the ith row and the jth column. Since that's true, for every row and every column, we've just shown that the entire matrices are the same. Okay, so we could finish our proof by saying something like this. Since I and j were arbitrary, we now know that the entire matrices, a plus b and b plus a, are equal to each other. Okay, and that's our proof.